Till now, we have seen cases where we had only one stress occurring at one time. For example, we had only the normal stress or the shear stress occurring in, let's say, the bending and torsion cases respectively. Now we will see the cases when we have combined loading happening, which means we have normal stress as well as the shear stress occurring in two dimensions. Such loadings have to be studied using what is known as a stress element. So the stress element looks like this. It's a two-dimensional element which has a length and the width, and we have stresses occurring like this as well as shear stress occurring like that. So these are normal stresses. These are called sigma xx and sigma yy. This is x, and this is the shear stress, which is given by tau yx and tau xy respectively, and this is x direction and this is y direction. Now here we know that the outward normal from the material, for example in this case, this is outward normal from the material. That normal, when it is along the positive direction of the coordinate system, that plane is called positive plane and the other plane is called negative plane. That is a convention which is followed. And we also know from the balance of moment caused by shear stresses that tau xy is equal to tau yx. This also is known. Now, obviously, now if I rotate my coordinate system by an angle theta, which means my new coordinate system becomes like that. So this is theta. So in this case, I should know what is the transformation rule so that I can alter my formula according to the transformed angle, which is so the transformation rule is given by this sigma x dash, for example, is given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta, where I have, for the sake of brevity, I have taken sigma xx as sigma x and sigma yy as sigma y for the sake of brevity only. This is what I have taken. So this is the transformation rule for the normal stress. Similarly, for the shear stress, we have another transformation rule. Tau x dash y dash will be equal to minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. This is the transformation rule for the shear stress. This is the shear stress. Now, in this case, for example, now if I, one more thing. If I take the other normal stress, so the acceleration stress is transformed to this one. There will be one sigma y dash also, which is the stress along the y direction or the transformed y direction. That will be given by sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sin 2 theta. This is the transformation rule for the y direction normal stress. Now from these two equations, let's say this is equation number 1 and this is equation number 3, sigma x dash plus sigma y dash is equal to sigma x plus sigma y. Now that's an important consideration, because if we know the sum of the two stresses at any particular orientation, we know that some of the stresses do not change. Some of the normal stresses, it doesn't change. That's a really important consideration to remember. Now let's see some important practical applications. Now we know that if we carefully see the shear stress transformation, it is possible to make make this shear stress 0 at a particular orientation of the coordinate system. So at a particular theta, it is possible to make the shear stress equal to 0. Such planes in which there is no shear stress are known as principal planes, and the associated normal stress values are called principal stresses. So the sigma principal stress values are given by sigma x plus sigma y by 2 plus minus square root of sigma x minus sigma y by 2 square plus tau xy square. These are the two principal stress values, because what happens is when we transform the plane, so if the plane becomes like this, so we have two principal, this is sigma p1 and this is sigma p2. There are two principal planes about which there will be no shear stress. So there is no shear stress here now. So the values of the two principal stresses are given by these numbers. Now even here, if we see sigma p1 plus sigma p2 is equal to sigma x plus sigma y. So you see this equation is again at play here. This equation, we have sigma x plus sigma y is equal to the sum of the two principal stresses also. Now if you have to figure out the angle at which this has happened, so the angle of the plane or the principal plane tangent to theta is given by 2 times tau xy by sigma x minus sigma y. So this tells us that it is possible to have this kind of orientation, which means I can transform my coordinate system by a theta p, which is given by this formula here, such that about those planes then I will have no shear stress, and such normal stresses, the stresses which are normal to such planes, are given by principal planes, or rather I should say that they are called principal stresses. Now, principal stresses are very, very important quantities in the design of various mechanical systems and devices. So please remember them very carefully. Now let's see what happens to the shear stress. Now we know that the minimum shear stress is always 0 because there is no shear stress occurring with on the principal planes, which means the shear stress in principal plane is 0. But it is possible to have principal stress or shear stresses rather, which are maximum. So what is the maximum shear stress which occurs? So the tau max is equal to, it is given by sigma x minus sigma y by 2 square plus tau xy square, square root of this quantity. Now like what we have got for the principal planes about which the principal stresses are occurring, which means there is no shear stress there, we can have planes about which the shear stress is maximum. So obviously we know that the minimum shear stress is 0, but there are planes about which shear stress maximizes. So those planes have shear stress which is given by maximum shear stress tau max, that is equal to square root of sigma x minus sigma y by 2 square plus tau xy square. So this is the maximum shear stress which occurs in that stress element, and the angle about which the shear stress is maximum, so it is given by tan 2 theta s, that is given by minus of sigma x minus sigma y by 2 tau xy. So this gives us the angle about which if we transform the coordinate system or rotate the element, we will get the maximum shear stress. Now obviously the maximum shear stress can be obtained by this formula also, sigma 1 minus sigma 2 by 2. This is obtainable by considering the previous transformation rule. So this is tau max. Now, why are these important? Why are we studying this subject at all? I mean, what is the use of studying transformation of stress? The first and most important use is it gives us the principal stresses. The principal stresses are very, very important consideration, because principal stresses give us the maximum stress which can occur in an element under any loading. So let's say I take a very simple example. I have this example, which is I have a plane, or I have a machine element which is having 100 pound 100 Pascal stress in x direction and 100 Pascal stress in y direction. Now, if I am supposed to design this, this will also be 100 and 100. Now, if I am supposed to design this machine element, and I am asked what is the maximum stress which occurs in any plane which is rotated about this the coordinates by any degree, what will I tell? I mean, that will be the maximum stress against which I have to design. So I figure out principal stresses then. So sigma p is given by sigma 1 plus sigma x plus sigma y by 2 plus and minus sigma x minus sigma y by 2 square plus tau xy square. Now, over here I know that I don't have any shear, so this becomes 0. Sigma x is equal to sigma y, so this becomes 0. So obviously sigma p1 is equal to sigma p2 is equal to 100 plus 100 by 2, that is 100. So I know that these are the planes. Right now whatever is being shown, those are the planes which are the principal planes also. So that is the maximum stress which occurs in the element. Now let's take the other case. Let's say I just transform this same problem to a relatively more complex problem, which is I have this 100, but I have this 50, and this is also 50. Now what is the maximum, or what are the principal stresses now? Now that's a relatively complex problem, because now I have sigma p1, or rather sigma p, the formula gives me sigma x plus sigma y by 2 plus and minus square root of sigma x minus sigma y by 2 square plus tau xy square. Now obviously now also there is no shear stress, so this is 0, but these are not 0 now. So the formula becomes 100 plus 50 by 2 plus and minus square root of 100 minus 50 by 2 square. So now this becomes 100 plus 50 by 2 plus and minus 100 minus 50 by 2. Now you see, now this 100 plus 50 by 2 is 150 by 2 is 75 plus and minus this value is 100 minus 50 is 50 by 2 is 25. So that value again is 100 or 50. So again these two are the planes which are still the principal planes. So you see, unless there is a shear stress applied, there cannot be a change in the principal stress. I gave the problems to bring in the point. Or in other words, we can say that about these planes there is no shear stress. Shear stress is 0. So these have to be the principal planes. Now let's see a really more complex problem. Now we take this problem now. We have an element which has shear stress occurring. That's it. There is no normal stress about this plane. Now this shear stress is, let's say the value of shear stress is only 1, whatever unit it is, 1 Pascal or megapascal or whatever. Now if I say what is the principal stress now, most people will think, why is this question being asked? I mean, there's no applied normal stress, so there cannot be any principal stress also. That is not correct. Let us see what is the value of principal stress. Now, we know that principal stress is given by sigma x plus sigma y by 2 plus and minus sigma x minus sigma y by 2 square plus tau xy square. Now, over here, we have no sigma x, no sigma y, so these become 0. These also become 0, but we have tau. That is not 0. Because that is not 0, it is 1. So, sigma p is given by plus and minus 1. Which means even in the case apparently which has no applied normal stress about a particular plane, there will be principal stresses and the value of them will be equal to the shear stress. Now let us see about what plane they are occurring. So we know that the planes are given by this formula, tan 2 theta p is equal to 2 times tau xy by sigma x plus sigma y. Is given by 2 into 1 by 0, which is infinite. So 2 theta p is 90 degree, which means theta p is 45 degree. So our planes are oriented with respect to the current planes by 45 degrees, which means if I have shear stress like this, then if I orient this thing by 45 degrees, which will be something like this, I will have only normal stress, and normal stress will be like this, because one normal stress is plus 1, so this will be plus 1, the other normal stress is minus 1. So we see the same element has normal stresses which are tensile and compressive in nature, but the value is equal to the shear stress value. Both of them are equal to 1 in terms of the number, but they are different in action, or they are different in form. One is compressive stress, the other one is tensile stress. So you see, apparently a problem which doesn't have a normal stress at all also has a normal principal stress. It has a principal stress. So that's a very, very important thing to remember. It may not be seen that there is a principal stress there, that there is a normal stress there, but normal stress, even in the absence of normal stress, even in presence of only shear stress, we will have normal stress about some plane. So it is very, very important to understand that you can vanish the stresses in one plane, but they will occur in some plane. Now, if this was designed without considering the normal stress, then the design would have been a disaster. Now, this is a very good problem to see because it clears a lot of fundamentals. Now, this problem shows that if there is only a pure shear condition, then about 45 degrees there is a pure normal condition, which means that the stresses, the shear stresses vanish at 45 degree orientation from the current direction. Now let's see some more, one more or two more problems about the stress transformation. Now in this case, now again, if I take a generic problem, now what is the generic problem? In generic problem, all the three stresses are occurring. So such cases will be obviously the ones which you can expect to be occurring in nature more frequently, because in nature all the three forces or the three stresses may occur simultaneously. So I have a case which is like this. I have a case wherein this stress is 2, this stress is 1, and we will not worry about the unit, it may be whatever, it may be Pascal or whatever it is. And there is a shear stress which is also equal to 1. Now let's see how to transform this case. So first of all, we have to figure out what is the principal stress. So sigma p is given by the sum of the two normal stresses plus and minus the difference of the two normal stresses by 2 square plus the shear stress square. So that becomes 2 plus 1, 3 by 2 is 1.5 plus minus square root of 2 minus 1 is 1 by 2 is 0.5 square. So it is 0.25 plus 1. So it is 1.5 plus and minus square root of 1.25. These are the two principal stresses. So sigma p1 is 1.5 plus square root of 1.25 and sigma p2 is 1.5 minus square root of 1.25. Obviously 1.25 square root will not be more than 1.5. It will still be less than 1.5. So both the principal stresses are positive here. But it is possible that you have one principal stress which is negative. We have seen that in the previous case where we had the pure shear condition. In that case, one normal stress was, or rather one principal stress was positive, the other one was negative. So we can have both the conditions. We can have both the principal stresses positive, and we can have both the one of the principal stresses is negative and the other one positive. But we can never have the condition which is both the principal stresses being negative. That condition is not possible. Obviously you can say it is possible, but in that condition both the stresses have to be both the applied conditions have to be compressive. Now that is also one very good condition to study. Let's see what is that condition. If you remember from fluids, from fluid mechanics, we have seen fluid statics. In fluid statics, what happens is we have the fluid element which is like this, and it is having pressure from all directions, PP, PP, like this. Now if obviously if you transform this this condition, this stress state, we will get sigma principal is equal to P, rather it is minus P by 2 plus minus square root of minus P plus P by 2 square plus, there is no tau xy square, there is no shear stress, so it is 0. So this whole thing becomes 0, so it is again minus P. So you see, that is the reason why we say that when there is a pressure, the pressure transforms into a pressure itself, which means that in case of a fluid, the pressure is equal everywhere. Throughout the planar element, pressure will be equal, which means that if you transform this element to like this, it will still have this condition only, pressure, pressure, pressure and pressure from all directions. So this condition is also an important condition to see, wherein both the applied loads are equal and in the same direction. Then the transformation doesn't change a damn thing, which means that it always transforms the elements to itself, which means the stress state doesn't change at all. There will be no induced shear stress and there will be no change in the value of principal stress. Principal stress will be equal to the applied force only. So the two conditions, the two extremes are one condition in which we have a pure shear condition in which we have transformation making the shear to go away become 0, and only two equal and opposite normal principal stress is occurring. But in the other condition in which we have a pure normal condition, which means the loads applied are equal and opposite normal stresses, so equal and in same direction acting normal stresses, in such condition transformation doesn't change anything, which means the stress state remains same to whatever angle you transform to.